In part 1, we built attention from queries, keys, and values, watched a word pull context directly from anywhere in a sentence, and patched the one gap that mechanism left open, positional encoding. That's the theory. This video is what happens when you actually stack this into a real, trainable network. The surrounding structure every real transformer needs, the cost this convenience quietly carries, and the modern LLM ecosystem that evolved from it. Welcome back to the Artificial Intelligence Institute Africa. Welcome back to the Artificial Intelligence Institute Africa, AIIA, pronounced Aiia, Ubuntu Guild's videos on AI. I'm Dr. Dennis Magaya, Chairman, Artificial Intelligence Institute Africa, AIIA. This is part 2 of our Transformer series. We're assuming you've watched part 1. Queries, keys, values, scaled dot product, attention. Multi-head attention and positional encoding are all prerequisite knowledge here. We won't rederive them. We'll build directly on top of them. Before we dive into the details, let me show you the road ahead. Welcome back to the Artificial Intelligence Institute Africa, Ubuntu Guild's videos on AI. I'm Dr. Dennis Magaya, Chairman, Artificial Intelligence Institute Africa. Let's start with Layer 1. Section 1, Training in Practice. Layer 1, the toolbox. The transformer block, residuals, and layer normalization. Part 1 described attention in isolation. Oh, the same device our CNN series introduced for ResNet. Output equals attention's result plus the original input, letting the gradient flow straight through the addition during backpropagation regardless of how attention's own gradient behaves, which suits the variable sequence lengths a transformer has to handle. The feed-forward sublayer. We are covering 3 layers today. Layer 1 is practical training, the structure that makes a transformer trainable, residual connections, layer normalization, feed-forward sublayers, causal masking, and KV caching. This is the toolbox that turns attention into a real network. Layer 2 is the mathematics underneath. Why scaling uses the square root of the key dimension, and why attention costs quadratically. Section 2. The mathematics underneath. Layer 2, the theory. Why scaling specifically uses the square root of the key dimension. Layer 3 is real-world application, the original 2017 transformer that introduced this architecture and the modern LLM ecosystem that evolved from it. This is the bridge to what you actually use today. Layer 1 is the toolbox. Layer 1 is the toolbox. Layer 2 is the theory. Layer 3 is the proof. Let's start with Layer 1. Section 1, Training in Practice. Layer 1, the toolbox. The transformer block, residuals, and layer normalization. As if a word's representation simply became its blended attention output. In a real transformer, it's added back to the block's original input via a residual connection. The same device our CNN series introduced for ResNet. Output equals attention's result plus the original input, letting the gradient flow straight through the addition during backpropagation regardless of how attention's own gradient behaves. After that addition, the result passes through layer normalization, which rescales the values at each position to a consistent mean and variance. After that addition, the result passes through layer normalization, which rescales batch normalization, which normalized across a batch of images. Because layer normalization instead normalizes across the features within a single word's own representation, which suits the variable sequence lengths a transformer has to handle. The feed-forward sublayer. Attention handles how information moves between positions, which words look at which. It does not by itself do much further processing of what a word means once that information has arrived. Every transformer block follows its attention layer with a small ordinary feed-forward network. Two fully connected layers with a non-linearity between them, applied identically and independently to every position. Recall the fully connected layer from our CNN series classification step. Recall the fully connected layer from our CNN series classification step. This is that same idea, just run once per word rather than once per whole image, giving each position a chance to further transform the information attention just gathered for it, position by position. Causal masking for generation. Part 1's attention, let every word look at every other word in both directions. Let every word look at every other word in both directions. That's one word at a time, as a language model does, breaks that assumption. At the moment you're predicting word 5, word 6 onward don't exist yet. And letting the model attend to them during training would let it cheat by looking at the answer. It's supposed to be predicting. The fix is causal masking. When computing attention for a given position, the fix is causal masking. When computing attention for a given position, every position after it is blocked from contributing at all, typically by forcing their match strengths to negative infinity before softmax so their weight rounds to 0. This preserves everything from part 1's mechanism, the same queries, keys and values, while ensuring generation only ever, attends backward, never forward, KV caching for efficient inference, causal masking. And just described isn't only what makes generation correct, it's also precisely what makes the following optimization safe. Recall from our RNN series. An RNN generates one token at a time cheaply because each step only needs the single hidden state carried over from the step before. A transformer generating one token at a time under causal masking faces. Because a masked position can never attend forward, the keys and values computed for every earlier position never change once they've been computed. An RNN generates one token at a time, cheaply, because each step only needs the single hidden state. A transformer generating one token at a time under causal masking faces, throwing away almost all of the previous steps' work. Here's where causal masking pays off. A transformer generating one token at a time under causal masking faces, the keys and values computed for every earlier position never change once they've. Because a masked position can never attend forward, the keys and values computed for every earlier position never change once they've been computed. And those ratings are used to train a reward model. The main model is then fine-tuned to maximize that reward. The keys and values computed for every previous position are stored once and simply reused. So generating each new token only requires computing that one new position's query, key, and value. Think of a village messenger who travels the same route to the next village every day. The first time they travel, the baobab tree, the river crossing, the rocky hill, they memorize the route. The next time they make the same journey, they don't relearn what they learned before and only focus on the new information. KV caching does exactly this. The keys and values computed for every previous position are stored once and simply reused. So generating each new token only requires computing that one new position's query, key, and value, and comparing the new query against the entire cache of already computed keys and values. Think of a village messenger. Once a word's key and value are computed, they are stored and reused. So generating each new word only requires computing the new word's query, key, and value. This is a pure engineering optimization. The mathematical result is identical to recomputing everything, but it's essential to making transformer-based generation fast enough for real use. Section 2. The mathematics underneath. Layer 2. The theory. Why scaling specifically uses the square root of the key dimension. Part 1 explained. Section 2. The mathematics underneath. Layer 2. The theory. Why scaling specifically uses the square root of the key dimension. Section 2. The mathematics underneath. Layer 2. The theory. Assume each entry in the query and key vectors is drawn independently with mean 0 and variance 1, a reasonable assumption near initialization. That scaling keeps softmax stable without deriving the, regardless of how large d sub k is. Scaled match strength equals query.key divided by the square root of d sub k. This is precisely the fix for the problem part 1 flagged conceptually. Without this specific scaling, larger key dimensions would produce larger raw dot products, pushing softmax towards saturation and its gradient towards 0. So square root of d underscore k isn't an arbitrary convenience. It's the exact factor that keeps the input to softmax at a consistent scale regardless of the model's dimensionality. Let's make that concrete with small numbers. Say d underscore k is 4, a query and key vector each with 4 entries. And say each entry independently has variance 1. Multiply the query and key entry by entry and sum the 4 products. Since each of those 4 product terms independently contributes variance 1, the sum of 4 of them has variance 4, not 1. Divide by a square root of 4, which is 2, and that variance is brought right back down to 1, exactly matching the scale softmax expects. More dimensions inflate the dot product spread by exactly as d underscore k grows, that raw dot products dividing by exactly the square root of d sub k rescales the dot product back down to variance 1, regardless of how large d sub k is. Dimension count and the square root of that same count is precisely what undoes it, the quadratic cost of attention. Recall part 1's central claim: every word attends to every other word directly in one step. That directness is exactly what creates this section's problem. For a sequence of length n, computing attention requires comparing every position's query against every other position's key in times and comparisons, each one costing computation proportional to the dimension of the vectors involved. Attention's cost therefore grows with the square of sequence length, not linearly with it. An RNN, by contrast, costs proportional to n directly, 1 hidden state update per token, regardless of how far back earlier tokens are, which was precisely the source of the vanishing gradient problem or RNN series covered. Attention traded that gradient problem away, but only by accepting an n squared compute and memory cost in exchange. Double the sequence length and attention's cost roughly quadruples. The 4 products. Since each of those 4 product terms independently contributes variance 1, the sum of 4 of them has variance 4, not 1. Divide by. To see these pieces work together, consider the original transformer introduced by Vaswani, Shazir, Parmar, and colleagues in 2017 for machine translation, the paper that introduced this entire architecture. The system used an encoder stack of 6 identical blocks, each containing multi-head attention followed by a feed-forward sublayer with residual connections and layer normalization around both. Its decoder stack mirrored the encoder but with causal masking applied to its self-attention so that generating each output word could only depend on words already generated, plus a second attention step letting the decoder attend directly into the encoder's output, resolving the exact context vector bottleneck our RNN series identified in the Sutskiver et al. System. The result outperformed the best prior RNN and CNN-based translation systems, while requiring substantially less training time, a direct consequence of attention's parallelizability across positions. Its main practical constraint was the quadratic cost. The original paper trained on sentence-level data, not the far longer contexts later systems would need to handle. The modern LLM ecosystem, from Transformer to ChatGPT. The 2017 Transformer was the breakthrough, but it wasn't the end of the story. Here's how the architecture evolved into the LLMs you use today. Decoder-only architecture. The original Transformer used an encoder-decoder architecture, but the dominant architecture for modern LLMs, ChatGPT, Gemini, Claude, Llama, is decoder only. For text generation, you don't need to encode a separate source sequence. You just need to predict the next word given the words that came before. The decoder's causal masking already handles this perfectly. So, modern LLMs use a deep stack of decoder blocks only, often 32, 64, or even 96 blocks deep, trained to predict the next token on massive text corpora. The attention mechanism is the same, it's just the architecture that got simpler. Pre-training and scaling laws. The transformer architecture was the key, but it wasn't enough on its own. The real breakthrough came from pre-training, training these models on enormous diverse text corpora, and the discovery of scaling laws. Researchers found that as you increase the model's size, the data set size, and the compute budget together, performance improves predictably and smoothly. This led to models like GPT-3 with 175 billion parameters trained on hundreds of billions of words. That directness is exactly what creates this section's problem. For a sequence of length n, computing attention requires comparing every position's query. Attention's cost therefore grows with the square of sequence length, not linearly with it, an RNN by contrast. The vectors involved. Attention's cost therefore grows, each one costing computation proportional to the dimension of the vectors involved, one costing computation proportional to the dimension of the vectors involved. Attention's cost therefore grows. Think of a village storyteller who learns from the elders in their own village. That's a small model. Now imagine they learn from every elder in the entire region, thousands of stories. Then the whole continent, millions of voices. With each expansion, their wisdom grows. That's pre-training and scaling. More data, more compute, more parameters, and the model becomes smarter and more capable. Fine-tuning and instruction tuning, but a pre-trained language model is just a next word predictor. It doesn't follow instructions or answer questions. The fix is fine-tuning, taking the pre-trained model and training it further on a smaller curated dataset of question-answer pairs or conversations. Instruction tuning teaches the model to follow natural language instructions, exactly what makes ChatGPT, Claude, and Gemini feel so responsive. Think of the village storyteller now being guided by a wise elder, learning to respond to questions and follow instructions. Reinforcement learning from human feedback, RLHF. Even after fine-tuning, models can still generate harmful or biased responses. And those ratings are used to train a reward model. The main model is then fine-tuned to maximize that reward. This transforms a raw language model into ChatGPT. A model that understands what constitutes a helpful, safe, and honest response. Think of the village storyteller again. At first they tell stories, but some are offensive. The community gives feedback. Over time, the storyteller learns what the community values and becomes a trusted advisor. That's RLHF, human. Think of a village where every person wants to talk to every other person directly. Think of a village where every person wants to talk to every other person directly. If there are 10 people, that's 100 conversations. Manageable. But if the village grows to 100 people, that's 10,000 conversations. Suddenly overwhelming. Attention works the same way. Doubling the sequence length quadruples the cost. That's the quadratic cost of attention, the trade-off for the power of direct connection. Deep stacks need the residual path just as much as deep CNNs did. Recall our CNN series finding a 56-layer plane CNN worse than a 20-layer one because backpropagating through many stacked layers compounds a shrinking local gradient at every layer, exactly mirroring the vanishing gradient problem across time steps. In an RNN, a stack of transformer blocks faces precisely the same risk simply from depth. The residual connections introduced in section 1 aren't a minor implementation detail. They're the exact same fix as ResNets. The residual connections introduced in section 1 aren't a minor implementation detail. They're the exact same fix as ResNets. Skip connections for the exact same underlying reason. A direct additive path guarantees the gradient can reach the earliest blocks undiminished, regardless of how many blocks of attention and feed-forward layers sit in between. Most of the world's largest language models are trained on English text. They struggle with African languages and contexts. That's why building African LLMs matters. Models trained on our languages by our researchers for our users. The translator who can turn a Hausa proverb into English without losing its meaning is using a transformer. The student who can access knowledge in their mother tongue is using a transformer. That is the work AIIA exists to support. For anyone pursuing chartered level expertise, these are the primary sources. Vaswani et al., 2017. Attention is all you need. The original transformer paper. Barr, Quiros and Hinton, 2016. Layer normalization. The normalization technique used inside every transformer block. He, Zhang, Ren and Sun, 2015. Deep residual learning for image recognition, the residual connection principle, Radford et al. In 2018. Improving language understanding by generative pre-training. The original GPT paper, introducing decoder-only transformers and pre-training. Ouyang et al. 2022. Training language models to follow instructions with human feedback. The paper that formalized the RLHF pipeline used in ChatGPT. Closure. Let's bring it all home. Layer 1, the toolbox. Residual connections and layer normalization structure every transformer block, letting the gradient flow through directly. Feed forward sublayers process what attention gathers. Causal masking blocks future words during generation. KV caching stores and reuses keys and values, like a messenger memorizing the route. Layer 2, the theory. Scaling uses the square root of key dimension because that's exactly what keeps the dot product's variance at 1. Attention costs quadratically with sequence length, like a village where conversations grow exponentially with the number of people. Layer 3, the proof. The 2017 transformer used all these pieces together to outperform prior systems. From there, the modern LLM ecosystem evolved. Decoder-only architectures, massive pre-training and scaling laws, fine-tuning and instruction tuning to make models helpful, and RLHF to make them safe and aligned with human values. Part 1 gave you queries, keys, values, scaled dot product attention, and positional encoding. This video filled in what sits between that theory and the models you use today. Residual connections, layer normalization, feed-forward sublayers, causal masking, KV caching, the square root scaling factor, the quadratic cost, and the modern LLM ecosystem. And here is why this matters for Africa. Sequences don't just exist in English text. They exist in African languages, in seasonal weather patterns, in the spread of livestock diseases, in the rhythms of the market. The transformer was the first architecture that could truly learn these patterns, that could pull meaning from anywhere in a sequence, regardless of distance, without fading. Most of the world's largest language models are trained on English text. They don't understand isiZulu, Hausa, Amharic, or the nuances of African culture. That is why building African LLMs matters, models trained on our languages by our researchers for our users. The translator who can turn a Hausa proverb into English without losing its meaning is using a transformer. The student who can access knowledge in their mother tongue is using a transformer. That is the work AIIA exists to support. That covers this series' foundation in full. From a single query comparing itself against a single key, to a complete working system, to the modern LLMs that have changed the world. Thank you for watching this Artificial Intelligence Institute Africa AIIA video brought to you by Ubuntu Guild. Subscribe to our Aiia YouTube channel and to Cognify.